So have you ever really thought about how we get energy from reserves that are buried literally miles beneath our feet? Well, today, we're going on that exact underground quest. We're going to dive into the incredible journey of what's called upstream exploration and production, or E&P for short.
It really all boils down to this one massive question. The best way to think about it is like a super high-tech, incredibly high-stakes treasure hunt. We're talking about using everything from massive sound waves to supercomputers just to find and pull resources out of the deep earth.
Now, to make sense of this whole complicated process, let's use a really simple analogy. Just imagine you're trying to get a drink of water from a well that is miles and miles deep. First, you have to find the water, right? Then you need an impossibly long straw to get down to it. And finally, you need some way to pump that water all the way up. That simple idea, right there, is the key to understanding this entire thing. So we're going to break this whole quest down into three main parts: the search, the access, and the harvest. So first things first, how on earth do you even start looking for something you can't possibly see? Let's jump into the search.
All right, welcome to Phase 1, the search. This is all about exploration. The big challenge here is figuring out how to map what's going on thousands of feet underground. And the trick? Well, we're basically going to use sound to see in the dark.
The main tool for this is this really cool process called seismic acquisition. First up is acquisition. This is where we send powerful sound waves down into the ground. These waves bounce off all the different rock layers and come back to the surface, kind of like an echo. Then comes processing, where incredibly powerful computers take all that data and build a detailed 3D picture of what's down there. And finally, you have interpretation. This is where geologists, real rock experts, look at that image for specific formations called traps. You can think of them as these little underground pockets where oil and gas might be stuck.
Okay, so let's say our seismic map lights up. We found a promising spot. But finding a potential trap, well, that's just the beginning. Before anyone is going to commit to a multi-million-dollar drilling operation, we have to know, is the rock itself actually any good for holding oil and gas?
You see, a good reservoir rock needs two absolutely critical things. The first is porosity. That's all about storage. How much oil or gas can the tiny spaces in the rock actually hold? Think of it like a sponge. But that's not enough. You also need permeability. That measures how connected all those little spaces are, which is what allows the fluids to actually flow. You got to have both for a successful well. No flow, no go.
And on top of that, we're also looking at other key clues, like the gas-oil ratio, which tells you how much gas is mixed in with the oil, and something called the water cut, which, you guessed it, tells us how much water we're going to get mixed in with the good stuff. These numbers are absolutely crucial for figuring out if a project is even going to be profitable.
So, we found our target and it looks really promising. Now comes the next huge challenge: the access. This is where some truly incredible engineering kicks in to actually get to the prize.
The goal here isn't just to drill down. Oh no, it's about drilling with almost surgical precision. We need to hit a target window inside that reservoir that could be just a few feet high, from miles away. And engineers have a great name for this sweet spot. They call it the bullseye.
And this just shows you how tricky hitting that bullseye is. To steer the drill bit, engineers plot out an exact path. They'll start drilling straight down, and then they hit what's called a kickoff point. That's where they start to curve the well. From there, they follow a very carefully calculated build-up curve to enter the reservoir horizontally, hopefully landing right on target. As the well gets deeper and deeper, it has to be reinforced. And this is done by installing these multiple layers of steel pipe, which are called casing. Seriously, think of it like building a tunnel straight down. Each layer has a really important job. The first few layers protect the ground and, crucially, any freshwater sources near the surface. The deeper layers give the well its structural integrity and seal off that final reservoir section.
Okay, we did it. We've reached our target. The well is secure. And now it's the moment of truth, the harvest. It's finally time to bring the oil and gas out of the rock and all the way up to the surface. So how fast is the oil and gas actually going to flow? Well, believe it or not, there's a fundamental principle of physics for that, and it's called Darcy's law. It's basically a formula that helps predict the flow rate based on the rock's permeability, the size of the reservoir, and the natural pressure that's pushing everything towards our well. At the same time, engineers are using a calculation called original oil in place, or OOIP. This is how they estimate the total size of the prize.
It gives them a really clear picture of the total volume of oil they think is in the reservoir before they even start producing a single drop. But here's a really common challenge. A reservoir might be chock full of oil, but if the natural pressure down there is too low, that oil isn't going anywhere. It's like having that deep well full of water, but no way to actually get it out. So, what do?
You give it a boost. We use something called artificial lift. This is literally the pump in our well analogy. Two really common ways to do this are gas lifts, where we inject gas down into the well to make the oil lighter so it can rise, and electrical submersible pumps, or ESPs, which are basically just powerful underwater pumps that push the fluids all the way to the top.
So once this raw mixture, which they call the well stream, gets to the surface, the journey still isn't over. It flows into a surface production system. Here, these huge vessels called separators do exactly what it sounds like. They separate the stream into oil, gas, and water. Then, each of those components is treated and prepared for storage or to be sent down a pipeline.
So, let's just take a final look back at this whole incredible journey. I mean, from listening to the echoes of sound waves bouncing off ancient rock to steering a drill bit with pinpoint accuracy miles underground, it is a truly massive, massive undertaking.
And it all just comes right back to that simple analogy we started with. Exploration was the map that helped us find the water. Drilling was us carefully placing the pipe to reach it. And production was the pump that finally brought that water up to our glass.
The scale and the sheer complexity of this whole process, it's just immense. And it's what keeps our lights on and our cars moving every single day. But it also makes you wonder, right? As our technology and our energy needs keep evolving, what will the next great quest for energy even look like?